So guys, now in this section we will going to understand TCP message demarcation. So we will going to understand what exactly TCP message demarcation is, why do we need it, and what problem does it solve. So we already know that, I assume that we know that TCP is a byte-oriented protocol. It simply means that the TCP sees the data as a stream of bytes. It recognizes no start or end of message in a stream of bytes. You can see in this diagram we have a sending process, and beneath the sending process running is the TCP protocol. So TCP runs at the transport layer and the process runs at the application layer. And you have a receiving process, and beneath the receiving process you have a receiving TCP running. You can see that the data which is generated by the sending process is pumped up into the circular buffers of a TCP protocol. So TCP maintains a circular buffer. Any bytes of data which is generated by sending process is buffered into this circular buffer first. And then TCP start dispatching this data from the other end of this circular buffer. Similarly, on the receiving side, TCP first buffer the data into its circular buffer, and then from the other end TCP start dispatching the data from its circular buffer to the receiving process. So here you can see that there is no notion of individual messages. Everything is happening in terms of bytes. Like a flow of water. So let's say an application on TCP process 1, that is this process, sends the message hello Abhishek to the TCP which is running on other machine, that is TCP process 2. Now it is not necessary that P1, that is the TCP protocol running beneath the process P1, will send the entire message to P2 in just one segment or in one shot. Let us say that the maximum segment size of the TCP protocol is 4 bytes. Now maximum segment size means we know that TCP exchanges the data by packing the data into some sort of packets called segments. Alright, so maximum segment size, that is the maximum number of bytes a segment can contain, let's assume that as 4 bytes. It is just a hypothetical example. So as I said, it is not necessary that P1 will send the entire message to P2 in just one segment. Because we have assumed that the size of the segment is 4 bytes, it means the entire message hello Abhishek would be splitted up into 4 segments. So it might be possible that the process which is running on the other machine will actually receive 4 segments, but in order. TCP maintains the order of bytes. We already know that. But here, a single message which was sent by the sending process has actually been obtained by the process P2 as 4 smaller messages, each of 4 bytes. So it simply means that a recipient process has no way to find out if the sending TCP has sent 4 messages of 4 bytes each, or it actually sent one message. So note that once again the TCP protocol recognizes no start or end of the message. All it sees message as a stream of bytes and nothing else. Let us discuss few more examples. Let's say in this slide you have a structure student, and the total size of this structure is 388 bytes. Right? Now let us suppose that the application running on the machine M1, let's say this is machine M1, this is machine M2. So the process P1 which is running on the machine M1 takes a variable of type struct student, fill this variable student with the name, roll number and address, and then the application invokes send2 in order to send the entire information of the student. Alright, so in a way the process P1 is sending 388 bytes. Now as I said, the TCP protocol works at the byte level. It has nothing to do whether the process P1 has sent the entire message as one single 388 byte long message. TCP can split the message into smaller segments of any random sizes. Let's say it is 100 bytes, it is 100 bytes, and this is 188 bytes. Alright, and when these segments are delivered to the application running on the machine M2, this information doesn't make sense at all. For example, first 100 bytes of the information doesn't make sense to the application running on the machine M2. You can see that in this structure, the name itself is 128 bytes long. So if the process running on the machine M2 receives the first 100 bytes of the message, it is not even a complete name, because name is 128 bytes long. So if you write the following pseudocode on the receiving side, then this code is bound to break. This code will work only when the underlying TCP on the machine M2 handovers the entire 388 bytes of the message in this buffer. Alright, then only you can typecast the complete buffer memory into the structure of type student, and then you can do whatever you want with that structure. But here consider a scenario where instead of 388 bytes, the TCP running on the machine M2 delivers just 100 bytes. Alright, so if you try to print this information after typecasting these 100 bytes into the structure student, you will end up printing garbage. Or if you do any other manipulation with this object student in this scenario, then your application may crash. So this will fail if TCP delivers the message in smaller chunks to the application on the machine M2. So thus TCP does not know where the message begins and where it ends. The TCP doesn't bother that this student structure is 388 bytes long. It will split the message into smaller chunks and then ship those chunks as individual segments to the process P2 running on the machine M2. So TCP, all it knows is that message is a sequence of bytes. And this problem is difficult to reproduce if you send only few bytes of messages between the TCP sender and the TCP recipient. Now you must be wondering that you may have written a couple of socket programs based on TCP, and you have successfully exchanged the messages between the TCP server and the client without seeing any problem. So the reason is that this problem is difficult to reproduce for smaller messages, but immediately reproducible for larger messages. Alright? If the message that is being sent or exchanged between the TCP sender and the recipient is just few bytes of the message, then this split of the message into individual segments may not happen, or it is very less probable to happen. The message will be delivered to the recipient as one complete chunk, and that is the reason that you might not have suffered this problem, because in all your programs that you have written, you must have exchanged the message of considerably smaller sizes. So question is how TCP can be used to exchange fixed size messages like most applications do. And so we will going to find the answer to this question in the subsequent lecture videos, and let us see one more example. So here again we have machine M1 and machine M2, and both running the TCP protocol. So TCP can also do the opposite. That is, the sending process P1 sends multiple messages in a loop. Messages can be unpredictably assembled together. So let's say that the process P1 sends the message M1, M2, M3. Now they are individual messages. And let's say this message is 100 bytes long, this message is 150 byte long, and this message is, let's say again 100 bytes long. So as I said, TCP works at the byte level. It doesn't care about the message boundaries. It doesn't care about the individuality of the messages. In this case, the process P1 is pushing three messages M1, M2, M3 to the underlying TCP on the machine M1. Now, TCP protocol running on the machine M1 can again pack these bytes of data into any arbitrary number of bytes. So let's say it may send two segments. One segment contain 250 bytes and other segment contain 100 bytes. All right. So here you can see that the messages are getting assembled together. The 100 byte and 150 byte is present in one segment, and the last 100 byte is in another segment. And I have taken these values randomly. It can be odd values. For example, first segment may contain 220 bytes, and the remaining 130 bytes can be sent in the second segment. Of course, this is the segment number 1, which is followed by the segment number 2. This is the segment number 1, which is followed by the segment number 2. Let's not forget that TCP maintains the order of bytes, but it doesn't maintain the boundary of the messages. So in the resource section, I have provided this URL. You can have a read of this URL, which explains the message boundary problem when it comes to the TCP protocol. And now in the next lecture video, I will show you a demo program in which I will show you exactly this problem. That is where individual smaller size messages gets assembled together into arbitrary number of bytes and then delivered to the TCP process P2.